Hello, my lovelies, it's Susanne, and today I want to show you how to solve this problem on exponential growth. A bacterial population initially consists of 1,000 bacteria. The number of bacteria doubles every hour. We have three parts that we have to solve here, so let's start with part A. Represent the number of bacteria after T hours as a function of time. This might sound a little bit confusing, but they actually just want us to find a function that gives us the number of bacteria after T hours. So when we're working with exponential growth, there is only one function that we're usually using, and this function looks like this, or it should look similar to this. I first write it down and then we take a look at it. So P of t equals P0 times e to the power of k times t. The formula you're using could look different. Maybe you're using different letters, so maybe it looks like f of t equals a times b to the power of t. So maybe like this, or even completely different, but it should have this structure where you have something times an exponential expression. And here the same thing, something times an exponential expression. So no matter how your formula looks, it should have this structure here. Let's take a look at the individual elements here, what they mean. P of t is always what we're looking for in our problem. So here we're counting the number of bacteria. They tell us that initially we have 1,000 bacteria, and then the number of bacteria does this and that. So P of t is always what this problem is about, and here it is the number of bacteria. P0 is always the initial number or initial amount of what we're looking for. If we're counting the bacteria here, then this is the amount, the initial amount of our bacteria. So here they tell us that we start with 1,000 bacteria. So this is our P0, our initial value. Then we have e to the power. This is just the exponential function here. T is our time. So time could be measured in seconds or minutes or hours, depends on the problem here. Here they're talking about it doubles every hour after T hours. So they tell us already that we want to measure our time in hours. So we will do that. And then we have this k in here, and k is the growth constant. It is not the growth factor. So if it tells us here it doubles every hour, this would be the growth factor. But the growth constant is related to that, but it is not what they usually give us in the problem. Okay, so the thing is that we have to find our function of time, so our t, which is our variable, will stay in this function till the very end. So we don't want to find something for t, but we want to find something for k and for P0. These are the two values that we have to insert here. So our function is going to look like P of t equals, what is P0? What is the initial number of bacteria? We already said this is 1,000 bacteria, so we can insert the 1,000 already for P0. And then we're going to multiply this by e to the power of k, the growth constant. We don't know it yet. We have to figure it out still. So I'm going to write it in here like this right now, and then we're going to multiply it by t. So this is how our function looks like now, and we still have to find our growth constant k. How can we do that? Well, if we insert something for t and for p of t, we could solve this equation then for k, to figure out k. What do we know about time and the amount of bacteria we have in our population? What do they tell us? They tell us initially we have 1,000 bacteria, but then the number of bacteria doubles every hour. So initially we have 1,000 bacteria. What does that mean after 1 hour? If they double every hour, then we're going to have 2,000 bacteria. So now we have a time here and a number of bacteria, and we can insert these things, the time for the time and the number of bacteria for the number of bacteria, and solve this equation then for k. So for the number of bacteria, we're going to insert the 2,000 on the left side. Then we're going to write down everything else. E to the power of, we don't know our k, it stays like this. But for our time, we're going to insert this 1 hour because it belongs to the 2,000 that we just inserted here. So time is going to be 1 hour. And now we only have to solve this equation for k. K times 1, we can just write it as k. And to solve for k, let's get rid of the 1,000 here first by dividing both sides of the equation by 1,000. Then we have 2,000 over 1,000 equals 2. And here this cancels out and only e to the power of k is left. If we want to solve for k, we have to get k out of this exponent here. And we have e to the power of k. We can get rid of this e by applying the logarithm on both sides of the equation. And I'm going to use the logarithm to the base e, so that is ln of 2 on the left side and ln of e to the power of k on the right side. And the ln and the e cancel each other out, and only our exponent here is going to be left on the right side. So we only have k on the right side, and we solve for k. K equals ln of 2. This is the exact value, and I would prefer to use the exact value. Of course, you can always put it in your calculator and get some decimal number, but this is more accurate. So I'm going to use ln of 2 for our k, so that our function p of t looks like this now. 1,000 times e to the power of, instead of k, we're going to insert ln of 2. This is my growth constant. And then I multiply this by t. We said t has to stay in this function because it is my variable. But this is the function they were looking for in part A. What do they want from us in part B? From now on, we are also allowed to use this function that we've just found. How many bacteria are present after 2.5 hours and after 180 minutes? Okay, this time we're looking for how many bacteria. So this is the number of bacteria is what we're looking for. After 2.5 hours, this is a time that they give us, and then they also give us a second time, so we have two separate calculations here. We start with the 2.5 hours first and take a look at this later then. So we get a time that we can insert for our t, And we're looking for a number. What is the number part here? That was this part here. That was the number of bacteria. So this is what we're looking for in this problem B. Okay, so let's just insert our t then. So we're looking for p of, and instead of our t, we're going to use the 2.5 hours. Important, our t was measured in hours, so we always have to insert hours, but we have 2.5 hours here, so it's okay to insert 2.5. And we're going to write down everything, but instead of our t, as soon as we get to our t, we're going to insert the 2.5 in there. And now we only have to put this thing in our calculator and let's calculate it. So the number of bacteria in my population after 2.5 hours is, and my calculator gives me a result of 5,656.85. How many bacteria is that then? 0.85. Is it 5,656 bacteria or 5,657 bacteria if I round it up? Well, I have 5,656 bacteria, and these 0.85 is not a whole bacteria yet. They haven't grown yet to one really strong bacteria. So I am not allowed to say I have more bacteria yet because they are not grown yet. So I only have 5,656 bacteria in my population after 2.5 hours. And then the second part of this part B, don't forget to do the same with the 180 minutes. But it's important, this is our time, yes, but it's minutes. We need this number in hours. So we have to take the 180 and divide it by 60 minutes to know how many hours this is. So we can cancel the 0. 18 over 6 equals 3. So this 180 minutes is 3 hours. And we can insert the 3 then into our t here and here. So this time we have p of 3. After 3 hours, we insert the t in here. So the 3 goes into our t. We put everything in our calculator, and this time we get a result of 8,000. So this time we don't have to think about is it 8,000 or 8,001. It is just 8,000 bacteria in our population after 3 hours. And the last part. After how much time will the number of bacteria have increased tenfold? What does tenfold mean? That means 10 times what we initially had in our population. So 10 times our 1,000 bacteria, which equals 10,000. So the question is, after how much time? So t is what we're looking for this time. We don't know t, but they give us the number of bacteria that we want to have at that time. So the 10,000 is the number of bacteria, and we know where to put the number of our bacteria. We have to insert it into this expression here. So instead of the left side, we're going to have the 10,000 bacteria. And we write everything else down because we are looking for the time. We want to solve this equation now for t. Let's get rid of the 1000 here first by dividing both sides of the equation by 1000, so that we have 10,000 over 1000 equals 10. Here this cancels out, and we only have our e to the power of this part here. This is how our equation looks like now. We still want to solve for t, so now I want to get rid of this e to the power here on the right side, and I can do that by applying the logarithm on both sides of the equation. I'm going to take the logarithm to the base e, which is the ln. So I have ln of 10 on the left side and ln of the entire right side here as well. So I have to write everything in here. So now on the right side, ln and this e cancel each other out, and only our exponent is what is going to be left on the right side. So I erase all of this. So this is what we had in the exponent is now here. We want to solve for t, so we have to get rid of ln of 2. And this might look weird, but actually this is just a number. So you can type it in your calculator, so you don't have to do anything special. We just want to get rid of it, so we divide both sides of the equation by ln of 2 here and here as well, so that this cancels out here and only our t is left. And on the other side, be careful, you're not allowed to reduce things here somehow. This is really ln of 10 over ln of 2, and this is how you put it in your calculator. And if you do that, you get a result of 3.3. This was the time in hours. So after 3.3 hours, we have 10,000 bacteria in our population. I hope it helped you. If you have any questions, please let me know in the comments. I wish you a wonderful day, and I hope to see you in one of my next videos. Take care!